Hello and welcome to another video where we are continuing our discussion on our introduction to statistical inference and hypothesis testing. We call that topic number 4. And for us to make things more manageable, I remind you that topic 4 comes in 3 parts. This will be the second one, which I'll number 4.2. The B indicates that this is our session where we do some problems, some examples by hand. Part A was the lecture portion, and B, where we do some problems, will come in 2 parts as well, just to make things extra confusing, where we do everything by hand using your calculator, and then I'll show you the alternative where you can use a spreadsheet to just have things be a little bit more convenient if you want that option. Many people aren't aware of the convenience of spreadsheets, just to act as glorified calculators, if nothing else. So a reminder of the book we're using. I love this book, Statistics for Psychology. Whether you are learning for reasons, psychological reasons, if that's your discipline or not, this book is still just wonderful. We are going to go to page 136. Scroll around a little bit to number 14 here, where we have 4 different studies. We won't do all of them. We'll do the first 2. Let's read the question to get an idea here. Based on the information given for each of the following studies, decide whether to reject the null hypothesis. For each, give the z-score cutoff or cutoffs on the comparison distribution at which the null hypothesis should be rejected, the z-score observed by way of the sample score given, and then our conclusion. It doesn't have to be in this order. This is just a rough guide. Assume that all populations are normally distributed. So this just gets us to get used to the idea without going through the full steps and the word problem for hypothesis testing and the whole procedure, which we will do. But right now we're just getting used to the idea here, visualizing it on the normal distribution, on the bell curve, and so on. So we want to look at study A. Let me say here number 14 is what we're doing. Study A, like so. So our null hypothesis, if you want to just write it down, is we're testing if our population, let's call it population 1, does in fact have a population mean of 5, and then our research hypothesis. Where's my book here? In this study A, we are predicting that it's higher, and so we have a one-tailed test. So our research hypothesis will reflect that it's in fact greater than 5. And then we have our sample mean. I'll call it mean here, or just a raw score, I guess. Well, it's fine. It's the same thing. Sample score, just a single score of 7. This is, let's rephrase that to an X, not get ahead of myself, 7. And the first thing, perhaps, regardless of what the question is, the order the question is giving me to do things, I might do B first. It's really A and B are somewhat interchangeable depending on what's more comfortable for me. We can change the raw score of 7 to the corresponding z-score that I'll call z observed. The observed z-score, to standardize it and see where on this normal distribution curve. Let's do a rough sketch. Oh, that's not that great. Let me do it in little pieces like that. Where on this am I sitting? Under the null hypothesis, this is centered at 5. raw score of 7. Where does that put me? Well, we have a population mean of 5 and a standard deviation of 1. And I'll draw your attention to the formula here, 3-1, which is the best one we have in the book. I know 7-7 looks similar, but we're not there yet, where we to calculate the z-score, we take the raw score minus the mean over the standard deviation, and this is now the population parameters instead. So we have our raw score. I'll write it like this for us. And what do we get? Well, let's write it in. We have our 7, population mean of 5, under the null hypothesis over 1. So we get an observed z-score of, it's an easy enough calculation, of 2. But I'll show that my calculator does work, just to give it something to do, right? Because it could be more complicated. So we'll test if it works, and it does. Ready for when the numbers may get more complicated. So this is our observed z-score. So this is a mu here of 5, which of course corresponds to a z-score of 0. So my observed z-score, I'll put dotted lines there. Z observed is 2. But the main idea behind hypothesis testing is, well, this observed score, is this considered extreme enough to suggest that the true population, by way of its mean, its position, is in fact not the 5 I thought it was? When do we consider it extreme enough or rare enough to suggest, to take it as strong enough evidence to suggest that the population mean isn't actually 5? Otherwise, I wouldn't just get these observations. We need a cutoff value or a cutoff score. So they want me to use an alpha of 5%. So let's write that over here. Alpha of 5%, or the decimal equivalent, means that, well, let's visually see what it means first. One-tailed test. So let's for a moment not be distracted by observation on the graph, because I don't know how it sits in relation to my observed score, and say, okay, I'm going to have a line here. That's going to be my cutoff z-score. So that in the tail will be 5% of all the scores, and then, of course, 95% of all the scores over here. Let me just move this a little bit so you can see the 5%. There we go. And 95%, of course, on the other side. That is what I decide beforehand, how I'm going to, what I'm okay with. There's a chance I'm going to make a mistake, and there are extreme, more rare scores possible, but only 5% of the time that's going to happen. So that's my cutoff that I decide beforehand. So I then look at this image and use my tables to find the cutoff score that would give me 5% in the tail. Let's go to our tables here. So we're looking for the second column here. That's exactly the tail we're looking for. And we're looking for 5% in the tail. So we're going to have to go quite a bit down, almost there. 5%, 5%, and we sort of get it in the middle of these two. Our table, unfortunately, gives us a 5.05 and a 4.95, not 5 exactly, unfortunately. Now, different people say different things here. Some say err on the side of caution and rather go to the more conservative one of the two. Others say just average the two out, we'll go with that one. But understand that with software, there are no gaps here. We do know everything in between. But in a book, they do give the shortened version, and you could run into the number you're looking for is in the middle of two that are given in the book. So we'll average those two and say 1.645. So our Z cutoff will be 1.645, but do understand that depending on the person you're talking to, depending on the book, they might choose one or the other and not necessarily average them. 1.645. Okay, so now let's put a box around that. I can use these two and compare them and say, well, my observed, move it a little bit over here, Z observed is further to the right of this cutoff line I was okay with working. If I see anything past this cutoff line, that tells me that this isn't just a fluke. It's because I got common values, but in fact, the true distribution is sitting a little bit further to the right, and these observations are actually more common. The mean isn't at 5, it is something more. I don't know exactly what it is, but it's greater than 5. Of course, there's a chance I could make a mistake, but I consider this evidence strong enough. So let's write our conclusion here. Our conclusion is to reject the null hypothesis in favor of the research hypothesis. And we can say a little bit more. The evidence is strong enough to suggest, fix my G there, to suggest that the population mean is greater than 5. So it's always nice to have some more words there to make it easy for someone to read your research results. All right. So that is the idea behind, the basic idea behind hypothesis testing that we'll refine and elaborate on as we continue. Next, I want to maybe leave this, make a new page so we can maybe refer back to this and see how everything is going to be very similar for the other study. Not exactly the same, similar. For study B, let's have a look at study B, where everything is very similar. We're testing the same population, mean, standard deviation, sample score is the same confidence level of 5%, but now we have a two-tailed test. All right, so let's see here. What was our layout here? I don't want to differ too much. Our null hypothesis, I know they don't specifically ask for that. We will be writing those in more detail as we get more practical problems, but it's a good reminder. We're testing to see if the population, the true population mean, is different from 5. So null hypothesis that it is equal to 5, research hypothesis that it is not equal to 5. So if I visualize the situation here, we have a normal distribution. Under the null hypothesis, we have 5 mean, or of course a 0 z-score. And now we have a two-tailed test. So we're going to have two cutoffs on either side. And if we use an alpha of 5% again, which the question wants, that means we're going to have to split the 5% between the two tails, and each tail is only going to have 2.5%. We only want to make a mistake 5% of the time. That's what we decide is good enough, and then 95% in the middle. So now when I try and find the observed z-score, not observed, sorry, the cutoff z-score, and I'm swapping things around a little bit from what we did previously, do the cutoff first maybe. We look up the z-score that gives us 2.5% in the tail, because it's a two-tailed test this time. So to go to my table, I'm looking for 2.5% in the tail, getting closer here. Oh, this time I got it exactly in the table. Of course, software will fill in all the gaps if you actually do the research properly. This is just an abbreviated table in the textbooks. 2.5 sits at 1.96. So now I'm going to write plus or minus 1.96. I have a 1.96 cutoff there. And of course, because of the symmetry, I have a negative 1.96 over there. Or you can make this a plus or minus. This is the positive one, and this is the negative one. So now I want to see, well, what is my observed standardized z-score? Well, I take the observed raw score, subtract the mean over the standard deviation. That's going to be 7 minus 5 over 1. Simple enough. It's a 2 again. In this case, the 2, let's zoom it in a little bit, will be over here. So this is my, oopsie, I needed to move that a little bit, 2.5% in the tail. This 1.96 is my cutoff z-score. This 2 is my observed z-score, and I see it sits further to the right, which tells me again that I expect just sort of common observations close to the mean. The majority of them will be close to the mean. Yet I get something this far out that is not a coincidence. That's strong enough evidence to suggest that maybe the true distribution sits a little bit further to the right in this case, but not at 5. I don't know what it is, but not 5. So my conclusion can only fit with the hypothesis that I set up. So if it was equal versus not equal, that's all I am looking at. I have to set up a new one to investigate if it's more, strictly greater, or strictly less. So let's say here, since my observed z-score is greater than the cutoff, positive in this case, or yeah, let's say it like that, we reject the null hypothesis, always in favor of the research hypothesis, and we can say the evidence is strong enough, and we decide beforehand what strong enough is by way of this confidence level alpha, to suggest that the true population mean is not 5. We don't know what it is. It's not 5. All right. So hopefully this gives you a good first introduction to thinking about hypothesis testing. We'll elaborate on this depending on the word problems we consider, and continue through the course, but with this idea at the heart of everything, really. All right, that is it for now. Until next time.